We'll talk about multiplex windings. We have been talking about simplex wave and lap windings in the previous few lectures. So we will switch to what are known as multiplex windings. Multiplex windings, as the name indicates, is the degree of multiplicity. So when you talk about degree of multiplicity in a multiplex winding, it's basically the relative number of parallel paths with respect to the number of parallel paths in the corresponding simplex winding. So if you are talking about a duplex winding, which may either be a duplex lap or a duplex wave winding, it basically has 2 times the number of parallel paths in as compared to a simplex lap or a wave winding. So what is a duplex lap winding? In the duplex lap winding, you have the commutator pitch YC is equal to plus 2 is equal to 2, and if you see the winding diagram, I mean the diagram of the coil, it looks something like this. You have the commutator segment 1 2 3 4 and 5 like this. So this coil side goes up like this, it goes up, and then this is the back side. It comes to side number 3. Let me just redraw the winding and draw the winding only first. And this is the second winding, second coil side. And this is the third coil side. So this is the way the coil sides are connected to the respective commutator segments. So this is 1 2 3 4 and 5. So if you see, the first coil side is connected like this, and this goes here and it is connected to commutator segment 3, and from this segment this is connected to commutator segment number 5. So the back pitch, which is the distance, like this, and this is the front pitch YF. So I've told you that the commutator pitch is 2 in case of the duplex lap winding. The winding pitch Y, capital Y, winding pitch Y is equal to twice the number the commutator pitch, and it is equal to 4. So for a progressive winding, the difference between YB and YF is plus 4, and for a retrogressive winding it is minus 4. Okay, so another thing that you must keep in mind is that these duplex windings may be singly or doubly reentrant. They may either be singly or doubly reentrant. What do you mean by this singly and doubly reentrant? A winding is said to be singly reentrant if after tracing the entire winding the starting point is reached. So you trace the entire winding, start from one point, trace the entire winding, and the starting point is reached again, and this is called a singly reentrant winding. In contrast, the doubly reentrant winding, the starting point is reached after tracing half of the winding. Starting point is reached after tracing half of the winding. In case of the singly reentrant, we have said that the starting point after tracing the full winding. Okay. So this was about duplex lap winding. Now in case of duplex wave windings, as in case of the lap windings, it is possible to have two independent windings in the armature. So in this case, the commutator pitch YC, it is made equal to C plus minus 2 divided by P by 2 instead of, so if you have the commutator pitch YC equal to C plus minus 2 divided by P by 2, so instead of this you use I'm sorry, let me rephrase this. If you have the commutator pitch as C plus minus 1 over P by 2, and you, instead of this commutator pitch, if you use the commutator pitch C plus minus 2 over P by 2, in this case, then what will happen if you pass around the armature once? If you use this commutator pitch and you pass around the armature once and you trace the winding, the connection will not be made. The connection will not be made to the segment adjacent to the one we started with. But it will be two segments away from the starting point, and this is evident. So you had the factor plus 1 here originally. If you increase that factor by 1, you are not going to end up in the adjacent segment, but it will be two segments away. Okay. So this is about the duplex wave windings. So similar rules apply. If you have the winding diagram of the if this is the duplex lap winding, you can similarly think of the duplex wave winding as well. Okay, and we will solve some simple examples on these windings in the class, in the offline class. But before we do that, after we will do that in the later classes, but right now I want to focus on what is known as the integrated approach for windings. So what we intend to do in this part is that we have to see certain basic relations and basic parameters, and once we see those parameters, we should be able to make the necessary winding calculations knowing these parameters. So what we'll do, we'll define certain parameters. We start with S, which is the total number of slots in the armature. P is the number of poles. C is the number of coils, and this is also equal to number of segments. YC is the commutator pitch. The CS is the coil span in terms of slots covered. Then we have an even integer. We use the word A for it, symbol A for it. U is the coil sides per slot, and this U is equal to 2C by S. Then we have another parameter, alpha S is the angle between adjacent slots. This is measured in electrical radians. Psi is the phase angle between EMFs of successive coils. This is again in electrical radians. Then you have the Y equivalent, Y equipotential. This is the equipotential pitch. Then you have the another parameter YPH, which is the phase pitch. Okay, so these are basic parameters. All of these parameters are easily, by definition, you'll be able to, just by looking at the definition, you'll be able to figure out what they actually mean. So one thing that we must always note is that whether the winding is lap or wave, the coil span, it must nearly be equal to the slots per pole. Slots per pole, or in short it is written as SPP. So the coil span CS should almost be equal to slots per pole. So if it is exactly equal to slots per pole, we mentioned that this is the full pitch coil, right? And if it is less or more than this, it's otherwise called a fractional pitch or chorded coil. So what we do now, we consider a full pitch coil. So we'll say consider a full pitch coil. So if you assume the flux distribution around the armature to be sinusoidal, I'll write it here for you. Flux distribution, we assume it to be sinusoidal. The EMFs will be sinusoidal, and if the EMFs are sinusoidal, the amplitude of EMFs can be represented by phasors. These are directional vectors. You would have studied them in your basic electrical engineering courses. So if we have a full pitch coil and we assume the flux distribution to be sinusoidal, then the amplitudes of the EMFs can be thought of as phasors. And if you have a situation where you have a winding which has two coil sides per slot rather, the angle between adjacent slots is given by pi p over s. How is this derived? We derive a figure for this. We look at a figure for this. So if you have a winding arrangement and the slot arrangement like this, So if you have if this is 1, 2, 3 and 4, and if this is the axis, then the angle between these two is denoted by alpha s. These 1, 2, 3, 4 are basically coil sides. Okay, so if you see, this is the coil side. So let me extend this finger further. This is 1, this is 9, this is 5, this is 13, this is 3, and this is the angle alpha s, and of course this is the side 7 and 15. I'll explain this in a bit. So for the time being, you just copy this diagram. And if you I should probably use another color for this. This is 1. This is, let me draw this like this. This is number 2. This is 4. This is 6. This is 8. 12. This is not needed. So this is 1, 3, 5, 7, 9 and 11. I'll explain this in a bit. For the time being, just draw this diagram. So if you follow this, let's leave this for the moment like this. Let's go ahead. When I say that this alpha s, this angle alpha s is pi p by s, how is this derived? This is electrical radians. Electrical radians. So this angle, you basically have to see the number of slots across the armature and then see the poles, and then you have to see that the entire armature covers a distance of 2 pi, which is 360 degrees. So when you divide this with the number of slots, you get this equation, relation alpha s, which is pi p by s. So this angle is also the angle between the EMFs generated in the two coil sides of the adjacent slots. So if you look at this figure which is shown in front right now, this is what is known as the EMF stars. The EMF stars, this is the figure for the EMF stars, where the firm lines, the lines which are not dotted, these represent the EMFs generated in the top slots, top layer of the winding, top coil of the winding. If you see, side number 1 is on the top here, side number coil side number 3 is on the top. So the dotted lines represent the EMFs generated in the top coil sides, and the dotted EMFs, which are represented by these dotted values here, 2, 4, 6, 8, 10 and 12, these are the EMFs induced in the bottom coil sides. So I'll write here, this firm line indicates EMF induced in top coil side, and the dotted indicates the EMF induced in bottom coil side. Okay, so this is clear that the EMFs in both the sides will be the same, so you can consider either one of the two. So the EMF in the top side is going to be similar similar to that in the bottom coil side. So since this has two layers, so it's easy to just consider one layer only. And then if you see the other figure, which I'm going to draw now, I will draw it for you here. This is E4, E5, E6, E7, E8, and if I say that this is some angle alpha, so this EMF star basically represents the EMF of the windings. If this represents the EMF of the coil side 1 lying in slot number 1, this represents the EMF in coil of the coil 2, which is lying in the slot 2. So this is represented like this. So you don't have to confuse this with this equation, with this figure. Here the numberings are different. We have the coil sides, 1 is here. If this is a slot, let me redo this. If this is coil side 1, if this is coil side 2, and this is 3 and this is 3 and this is 4. So this E1, E2 is basically the EMF generated in the coil lying in the side slot number 1, and this E2 is the EMF induced in the coil lying in the slot number 2. Okay, so you don't have to confuse it with this numbering scheme here. So this E1 and E2 are different. Okay, so after we draw this figure, if we have so you have to know that this E1, 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 E2 and E up to E8, these refer to the these numbers refers to the coils or the slots and the EMFs generated in the respective slots. So what we do, we basically have another situation where we Going further, we will take a case where this u, the parameter u which we discussed earlier, which is the coil sides per slot, we take this u to be equal to 2 for simplicity. This is the case where we have two coil sides per slot. So in this, when this u is 2, what happens? The all coil sides in the same slot have same EMFs identical in phase and magnitude. These EMFs are same in phase as well as in magnitude. So if you have another case, another case would be the case where you will have u equal to 4. You would have 4 coil sides per slot, or in that case as well you will have slots having the same EMFs, which would be in phase, and you would have coil sides being equal to having EMFs in phase and in magnitude, as well as in identical in phase and identical in magnitude as well. Okay, so if you then see the conditions for a closed winding, so when is a winding considered to be closed? If you have a winding with u equal to 2, so a two-layered winding, and C equal to S, and this winding is connected electrically in series, such that no circulating currents flow, this winding is said to be closed. When will this current flow, this circular current, be equal to 0? This will happen when there is no resultant EMF around the armature or either this should be case number 1, that the resultant EMF around the armature is either 0, or the resultant EMF of all the coils should be equal to 0. The winding in this case is said to be a closed winding when summation of the EMFs is equal to 0. Okay, so what would happen in such a case? Let me draw the EMF star for you. The EMF star in such a closed case would be something like this. Okay, So this is E1, this is E2, E3, E4 and E5. So this would be E7. Then we would have a winding here, EMF here. This would be E8. This would be E9. This would be E10. Then you would have sorry some winding, let's call it EC. So this would be E5, sorry, this would be E6 rather, and this would be EC minus 1. So what we do in this case, this is the EMF star for a closed winding. So what we have, the resultant of this EMF is 0 when you have the summation 1 is to C of psi, which is equal to C psi. So what is psi? We discussed this psi earlier. This psi is the phase angle between the EMFs of the successive coils. So if the phase angle, summation of the phase angle is equal to C times the phase, I mean it will be C times the this phase angle. So what is this? This is 2 pi, 4 pi, 6 pi, or in general alpha pi. So if the summation is equal to C times the phase angle, then in this case what happens, this alpha, which is said to be an even integer, which we discussed earlier while introducing this. So 2, 4, 6, etc., etc. So for a closed winding, what we would basically want is U equal to 2 and C equal to S. So if you see the relation, S times the number of slots times the angle between the slots is equal to S times P, and C psi is equal to pi times A. Sorry, this is alpha A, so this is equal to A pi A. So alpha S over psi would be equal to P over A, or this psi would be equal to A over P times AS. So this is the equation or the relation for the winding to be closed. You can find out the value of this, the phase of the angle, the phase between the phase angle psi, if you know this value A, which is the odd integer, sorry, even integer, and let me go back and check what we have defined. A is an even integer. All right, so if you define, this is alpha S over here. Okay, so even integer A, P is the number of poles, and alpha S is the angle between the successive segments. So this basically, this equation gives you the relation for a closed winding. Okay, all right. So in case of this winding, uh, this is the winding diagram when you have uh, two coil sides in one slot. I forgot to mention it there. I actually had to show you a situation where we would have four slots, four coil sides per slot as well. So that figure is going to be something like this. 3, 4, 5, 6, 7 and 8. And in this case, this would be the angle between the successive coil sides, alpha s, between the adjacent slots. So this is the four coil sides per slot. Okay, and in this case, this is the EMF star. For this case, you this is the EMF star for this case. You see coil side in 1, E1, E2, so sorry, this is not related to the 4. Where did I keep it? So this is the four coil sides per slot. So the EMF star for this would be something like this. What it would be like? Yes, it would be 1 and 3, 5 and 7, and this would be the EMF star for this this four coil side per slot arrangement. All right, this figure is the EMF star. I label it again, EMF star for a closed winding. So this is a bit difficult to understand, so that's why I made a video for it, for you to see at ease, and you can watch it again and refer to the book as well, because this would be slightly difficult to understand in one class. So since this was a slightly bigger topic, that's why I made a video for it. So I hope this is clear. I will try to understand this again in the offline class, but I hope you will see this video in time. And that's it for this lecture. I will see you in the next class now. Thank you.